Hello and welcome to this Haas Tip of the Day. In today's video, we're going to talk all about speeds and feeds. We'll show you the path that we take to reach starting speed and feed values that we can trust, that will work with any tool and material combination. We'll be using metric values in this video, but have made another video for those of you that are running inches. A few key concepts, a formula, and we'll reach the RPM that our program needs. Another quick calculation, and we'll establish our feed rate and have you home in time for supper. As we jump into one of the coolest concepts in CNC programming, speeds and feeds, I've got a question for you. Are you ready? If our tractor is moving along at an amazing 1 kilometer per hour, that's roughly 17 meters per minute, which tire is moving faster? Our small front tire or our larger rear tire? Everything for me begins with my setup sheet. So check this out. I've got a block loaded up. Now if you're tightening up those tools by hand, that's it. Pencils down. Answers? I know. It's kind of a trick question. It depends on what I mean by faster. If what I am asking is how fast the tires are moving across the surface of the ground, where the rubber meets the road, then both tires are traveling at the exact same speed, 17 surface meters per minute. See, both tires travel the same distance, where it matters, along the tire's edge. Now, if we're talking about revolutions per minute, RPMs, then that's a different story. While both tires cover the same amount of ground, the smaller tire had to make more revolutions per minute to get there. If we want to calculate how much ground a tire will cover with each revolution, then we'll need to come up with some kind of ratio between a tire's diameter and its circumference. Well, it turns out someone has already figured this out for us, and they've even given this ratio a name, pi. The ratio between a circle's diameter and its circumference is pi. So no matter what diameter our tire is, the distance around the outside of that tire, where the rubber meets the road, is always 3.14 times greater. This tire, at 100 millimeter diameter, has a circumference of 314 millimeters. 100 times pi is 314. Now this tire has a diameter of 1 meter and a circumference of 3.14 meters. 1 times pi equals 3.14. Okay, back it up, get out of here. If we were to run our tires too fast, too many surface meters per minute, they would overheat, blister, and fail. Our end mills work in the same way. There's a limit, a maximum cutting speed that a specific tool can go on a specific material. Any faster, and it begins to overheat and quickly wears out. In machinist talk, if we're talking about speeds, like speeds and feeds, we could be talking about one of two different things. We're either talking about cutting speed or spindle speed. Our cutting speed, VC, is our surface meters per minute. The speed our tool is turning at where the rubber meets the road, where the tool meets the part. And our spindle speed is simply our revolutions per minute, our RPM. We'll get our tool's cutting speed in meters per minute right from our tool catalogs. But to control the Haas machine, it needs an RPM value, a spindle speed. That's our S code. To get from here to here, we're going to use a formula. And that formula is going to make use of pi and our tool's diameter to convert our meters per minute into an RPM value, a spindle speed. Now, once we've got that RPM value, we can calculate our feed rates, speeds and feeds. Here is our formula to calculate our RPM. Now, I'm going to start using some symbols, some notation, because those are the symbols being used by all of the tool suppliers now, and you'll need to recognize them. RPM equals cutting speed times 1,000, all divided by our diameter times pi. N is our RPM, revolutions per minute. That's the S code in our program, what we're trying to solve for. VC is our cutting speed, are surface meters per minute. D, or sometimes DC or D1, depending on the catalog, is our tool diameter in millimeters. The 1000 in this formula is there to convert our meters per minute into millimeters per minute. This formula works fantastic, but we're going to simplify it a bit using algebra. We're going to divide the 1000 by pi. 1000 divided by pi is about 318. We're going to go ahead and use this simplified formula for the rest of the video. Before we open up our catalog and get our cutting speed, before the tractor even leaves the barn, we need to know exactly what cutting tool we're going to use. And we need to know exactly what material we are going to be cutting. Now, in the good old days, all we really needed to know was whether our end mill was high-speed steel, carbide, PCD, or CBN. Those days are gone. Today's tools have coatings on them that might double their allowable cutting speeds. So we really need to know what tool we are working with. Otherwise, we'll have to use really generic values, which are pretty wimpy. With our exact tool number in hand, we can go to our tool catalog. We can download the manual for any tool manufacturer in PDF form. Once that catalog is opened up, we're going to search for the material group section. That's going to tell us what material group our exact material falls into. Our materials are color-coded. P is for steels, M is for stainless steels, K is for cast irons, N is for non-ferrous metals without iron in them, like aluminum or magnesium. S is for our super alloys, materials like titanium, and H is for hard cast irons or hardened steels. I am working with a 4140 steel. At least that's what we call it here in the United States. If you're in Europe and you're using EN names and numbers, this might be called 42CR-MO4. If you're in Japan, you'll call it something different. But no matter where you are in the world, this material is going to find itself in the P ISO material class. Now, the number that follows our color-coded ISO letter changes between manufacturers, so be careful here. Kennametal calls this material a P4. Niagara and Seco may call it a P5. Sandvik classifies it as a P2.1, while Iskar and Whittia might call it a P6 or a P7. Same material, different tool vendor. Now, it's important that we get this right. If you don't choose the right material group, you are going to burn up your tools. Titanium has a different machinability than mild steel. If you try running a drill or an end mill in titanium at cutting speeds meant for mild steel, you are going to melt that tool. It will overheat and fail. So, if you can't find what material group your stock should be in, then give your tooling representative a call. They would love to hear from you. How many tooling reps out there would love to hear from one of our viewers and talk tools? Yeah, that's what I thought. From the section of the manual for our exact tool, under the row that lists our material group, P5 in our case, we're going to find our cutting speed, our VC, our meters per minute. If your catalog gives you a range of values there, then you'll make your choice based on the length of your tool, how strong your setup is, and how aggressive we tend to cut. In general, the more rigid the setup, the faster we can go with our cutting speeds. But remember, tools tend to last longer, have better tool life at lower cutting speeds. For my tool and material, we're going to use a cutting speed of 100. That's 100 meters per minute. I'm using a 20 millimeter end mill, so we'll drop in 20 there. And after a little bit of math, we come up with an RPM value of 1,592. So our S code back in our program is going to be S1592. We now have a cutting speed, an RPM value that we can use without our tool. Exactly. We now know how fast to spin our tool, our speed. The control now needs our table feed, our F code of feed rate. The feed rate is how far the tool will travel in 1 minute in millimeters along the tool's center line. Here is our feed rate formula for end mills. We've got our table feed equals our feed per tooth times the number of teeth times our RPM. So what's a tooth? This is a tooth. It's just a cutting edge along the outside of a tool. An insert is also a tooth. For most tools, the number of teeth matches the number of flutes. This tool has 3 flutes, 3 teeth. This tool's got 6 teeth, and this one's got 4. We want our tool to take a very specific size bite with each tooth. This is our feed per tooth in millimeters. Just like our cutting speed, the book, or PDF, will give us that feed per tooth value. The catalog says that for my tool, material and type of tool path, 0.08 millimeters per tooth is a good starting range. 0.08, our feed per tooth, times 4, our number of teeth, times 1,592, our RPM, will give us our millimeters per minute feed rate, F509.44. Again, this is how far the center line of our tool will move along its programmed path in millimeters each and every minute. Some manuals will just give out a single feed rate for all cutting conditions, but most will give us at least 2 possibilities, one for slotting and one for side milling. Our AE is our width of cut, that's our step over, that's our radial depth of cut, and our AP is our axial depth of cut, how deep the tool is moving in the Z-axis. Most times, if you're slotting, your bite is going to be about 25% less than if you're just side milling. With the popularity of optimized tool paths like dynamic, adaptive, volume mill type high-speed machining tool paths, the tool manufacturers are getting more and more specific with their speed and feed recommendations. So you'll often see charts like the one we'll show you here listing all kinds of different tool paths. You'll choose one and then match your speed and feed to the path that you're using. Now, if you are dealing with drills and not end mills, our feed rate might be listed in our catalogs as a feed per revolution and not a feed per tooth. We just multiply the millimeters per revolution chip load from the book times our RPM to get our feed rate in millimeters per minute. Now watch out for and know the difference between millimeters per tooth, FZ, which we typically use for milling tools, and millimeters per revolution, FN, which we often use for drills. Here is that completed legend and the formulas we typically use for calculating our speeds and feeds. We've got our cutting speed formulas, spindle speeds. We've got our feed rate formulas for both end mills and drills. And we've got all of the notations, all the symbols that you're going to see over and over again in your tool catalogs. With all of that said, there's a big shift happening with tooling catalogs in general. A lot of these tooling catalogs are just giving us our feed rate and RPM values. No formulas needed. You may open up your manual and find that you don't have to do any math at all. Okay. In the past, we used to have to rely on slide rules to calculate our RPM and feed rate. I still like these, I think they're great. But today, we're more likely to use an app on our phone or a piece of software on our computer, or the speeds and feeds calculator right on the Haas control. On machines with next-gen controls, you can reach the milling calculator by pressing current commands and navigating to the milling tab. We've made some videos that help you calculate those tapping feed rates. We'll link to those in the description. Well, that's it. Let's go home. You can call your tooling rep in the morning. Well, thanks for letting us be a part of your success and for watching this Haas Tip of the Day.